guys, and welcome back. We're still talking about we still got some stuff to do with systems of equations, so we're still in chapter 5. But today we're going to talk about a different method, the only other method in this textbook that we talk about for solving systems of equations algebraically. It is called elimination. I think I might have mentioned this in some of the last videos we did on substitution. It does come from section 5.3 in the textbook if anybody does still look in the textbook for anything. And I'm sure you could absolutely Google this or put it into Khan Academy, solving systems of equations by elimination, or even solving systems of equations by substitution from the last couple of videos. I'm sure you'll find a ton of stuff about it. The idea behind both of these methods is pretty universal no matter what places you go to on the internet to look for this kind of information. Basically, the whole idea, since we're still talking about systems of equations, the end goal is still the same, right? We still want to somehow work with both equations so that we're left with one single equation in one variable that we can then solve, plug it back in, and get the other variable. Our end goal is still going to be two parts of our solution, one x value, one y value that we would then combine to write as an ordered pair. The way we're going to go about that is different, obviously, since we're talking about a different method called elimination. I think there's a little step-by-step guide in a couple slides, but basically the idea that they're saying here is, well, let's say you're given this system, right? The idea that they're coming up with is the fact that if you combined the like terms for both of these equations, like if you just kind of added up the x's, the y's, and then the constants on the right-hand side, what would happen, especially with the y's, is the fact that the negative 2y plus 2y, well, negative 2 plus 2 cancels out. So if you added up the like terms and just kind of combine the equations together, if something like this happens, what you would be left with in this case, let's say, is 6x equals 20. Now, I wouldn't give you something like that because when you try to solve this for x, you would wind up with a decimal. But that's kind of the idea that they're going for, is we're going to try to manipulate these equations somehow so that one of the variables cancels out like this. Negative 2, positive 2. Negative 3, positive 3. Something like that. It's all because the idea is about balance, right? Was that supposed to say negative 19? I guess it was supposed to say negative 19. All right. If it said negative 19 instead, they're talking about this idea of balance, right? When you combine, it's kind of like whatever you do to one side, you have to do to the other. If you combine the equations on the left, you have to combine the equations on the right. I guess it was supposed to say negative 19, but this is kind of going into what I was just saying before. When you combine both of those equations, negative 2 and negative 2y and 2y cancel out. So that's what you would be left with. You could then solve for x and then do the exact same thing that we did when we solved a system by substitution, where you would take that x value and plug it into either one of these two original equations to get your appropriate y value. What else does this say? Align all like terms, so make sure all of the x's are lined up vertically, all of the y's are lined up vertically, and all of the numbers are also lined up vertically. I think most of the systems that you guys will see already do look like that, but just be aware that you might still need to do a little bit of rearranging to make sure all the x values and the y values are lined up if you're solving by elimination. So the ultimate goal is, again, you have freedom of choice with elimination. You can still pick which variable you want to eliminate, either x or y. There are certain situations where eliminating one variable is going to be easier than eliminating the other. But the ultimate goal is to get the coefficients of both of those equations for that variable to be, what word did they use? What did they use? Opposite coefficients. So same number, opposite sign, kind of like the negative 2 and the 2 from the y's earlier. The way we would manipulate something like that is by multiplying the equation, which we'll see a little bit later in other examples. So we might have to do a little bit of multiplication first, but then you would be able to eliminate that variable and then solve the equation like you normally would, and then do the same things like I said, that you would do for solving a system by substitution. Plug your value into either one of the two original equations, and then get your other variable, and then write your final answer as an ordered pair. So I feel like I've just been talking for 5 minutes, and I honestly don't know if any of this is making any sense. So let's just kind of go into an example. All right, so this is, I think, the simplest type of solving a system by elimination problem that you're ever going to see. Because if you look at the y's, it looks very similar to the negative 2y and the positive 2y from that given example. We have a negative 4y and a 4y. So if we just went ahead and added these two equations, just kind of combined all the like terms for the two equations, just squish them together, negative 4y plus 4y cancels out. So when we do the same thing for the x's and for the coefficients, 3x plus 1x is 4x, equals 10 minus 2, because this is negative, is 8. So now the y is gone. All right, that was the goal, to eliminate not necessarily the y, but either the x or the y. And that's what we just did here. All right. So now we can continue to solve for x by dividing by 4, and x is going to be 2. So we have our x, and then we still need a value for y, so we would do the same thing that we did for substitution. We would take this 2, plug it into either one of these two equations, it doesn't matter which one, for x, and then solve for y. All right, I'm going to pick the second equation just because it's a little bit less work, just because there's no coefficient in front of the x. So I'm going to do 2 plus 4y equals negative 2, and then solve that for y. So we do that, divide by 4, and y equals negative 1. So there's our x, there's our y, and same exact thing like we would do in substitution. We're going to write our final answer as an ordered pair. So x comma y, 2 comma negative 1. And that's the basics for solving by elimination. If this did also say check your answer, I would be looking for the extra work to plug the x and the y in for both equations, and then just making sure that you do get equals 10 equals negative 2. And if it doesn't, or if you don't, that's a pretty good indicator that you're doing something wrong. All right, pretty much exactly the same. The order is just a little bit different, not a big deal. Y comes first. The point is still the fact that you have positive 3x and negative 3x. So when you add these up, positive 3x and negative 3x are canceled. The x is getting eliminated this time. So y plus 2y is 3y equals negative 2 plus 14, which is 12. And then it's the exact same thing, you're just solving for y instead. Divide by 3, y equals 4. We're going to plug 4 back into either of the two originals. I'm going to stick with the first one this time, just again for the same reason as the last one, because it's just a plain old y, there's no coefficient on it. 4 plus 3x equals negative 2, minus 4, 3x equals negative 6. Divide by 3, so x equals negative 2. And if something like this happens where you end up solving for y first, just again, when you write your final answer as an ordered pair, it's still always got to be x comma y, so it's negative 2 comma 4 instead of 4 comma negative 2. All right, so that's the basics. Slightly more complicated is, well, if they have the same coefficient but the same sign, they are saying you can subtract one equation from the other. To subtract an equation, add the opposite of each term. So that's definitely one way you can reason with it. Another way I reason with it is multiplying either equation by negative 1. It's the exact same thing as subtracting. So here's what I'm talking about, right? If you look at the x's, 2 and 2, right? We would be able to eliminate the x's if either one of these 2's were negative. It doesn't matter which one. So as long as we make one of them negative, like let's say we made this first 2x negative, that would make our lives a whole lot easier. But if we make this first one negative, if we change its sign, we have to change every single sign in this first equation. So that's why I say, at least for me, it makes more sense to multiply by -1. So then if I write it like that, okay, well now I know I have to distribute the -1 to everything in the equation. All right? You could absolutely do the same thing for the second one. All right? Like I said, it doesn't matter which equation you make that -2x, as long as you do it to only one, because we want one positive, one negative, and as long as you make sure you change every single sign in that equation. So if I did that for this first one, I'm going to rewrite this right under the second one. That's part of the reason also why I chose the first one, because just because it's less writing. We would have -2x minus y equals +5. And now, if we work with these two equations as the system, 2 minus 2 cancels out. And then we can do the exact same thing with the y's. -5y minus y is -6y equals 13 plus 5, which is 18. And then we solve. Y is, -3. And then we're going to plug -3 back into either of the two originals. Same thing, I'm going to go with the first one. 2x minus 3 equals -5. Plus 3, 2x equals -2. Divide by 2, x is -1. So those are the two parts of the answer to our system now. -1, -3. Excuse me. All right. Same thing here, we're just dealing with the y's now. All right, it would be great if the 3's right here had different signs. That would be fantastic. So why don't we make them have different signs? I'm going to do the same thing I did with the last problem. I'm going to switch the signs of this first equation. So I'm multiplying it by -1 and then just writing it directly under the second one. So this becomes -3x minus 3y equals -15. The y's are then going to cancel. This is -5x equals -20. And then we solve. So x is 4. Plug it in. There are coefficients for all of them this time. So the second equation has slightly smaller numbers. So I'm going to plug the 4 into the second one. Again, it really doesn't matter which equation you plug this 4 into. You should get the exact same thing either way. So I'm going to do -2 times 4 plus 3y equals -5. So this is -8. Add 8. 3y is 3. Divide by 3, y is 1. So there you go. 4, 1. All right. So that was kind of like the little intro to the whole multiplying aspect of a system. But what's the word I'm looking for? I guess, meat of it all is when you actually would have to multiply one or both of the equations by a number, not just -1, so that one variable has opposite coefficients. Sometimes, actually, let's just kind of go into a problem. All right. So again, our goal here is pick a variable, doesn't matter which one, and we want to multiply one or both of the equations so that variable, both of those variables have the same number but opposite signs. So if we already have opposite signs, that's probably going to make our life a little bit easier. Like the x's, right? It's not the same number, but one is positive, one is negative. So again, it really doesn't matter which one you pick, but I'm going to pick x to eliminate just because I already have one positive, one negative. But I don't have the same number. So how do we think about what number we're going to multiply by? One way you can think about it in general is LCM, or least common multiple. I want that coefficient then in front of both of these to be the least common multiple of both of those coefficients. So we're going to keep it this positive, this negative, but I want the number in general to be whatever the least common multiple of 1 and 3 is. Or just any multiple, really. But the least common multiple of 1 and 3 is going to be 3. So I want these both to have 3 as a coefficient, and I want one to be positive and one to be negative. Well, this one already has a negative 3, so that makes our lives a little bit easier. We need this one to have a 3, though, particularly positive 3. So how do we get positive 3 from 1 by multiplication? We multiply by 3. And same kind of thing like we did before with the negative 1. If we're multiplying x by negative 3, we have to multiply everything in the equation by 3 as well. Did I say negative 3? I meant positive 3. We're multiplying x by positive 3, which means we're multiplying everything in the equation by positive 3. All right? Since we're not doing anything to this second equation, I'm going to leave it alone, and then I'm just going to work with this. 3x plus 6y equals 33. And then if we try to add these two up, negative 3x plus 3x cancels out, and then everything else is exactly the same as it was before. This is 7y, and this is 28. So now we can solve. And then the rest of it's the same. Plug 4 into either one. I'm going to do the second one because, again, there's no coefficient on that one. So negative 3x plus 4 is negative 5 minus 4. Divide by 3. So x equals 3. And then we write our final answer as an ordered pair. Okay. So this is I think, probably the most complicated type of problem that you're going to see for something like this. All right? If we just kind of look and see what we have, well, again, we have x with already opposite signs. Not the same number, but opposite signs. So that's half the battle. So since we already have half the battle done for x, I'm going to pick x as the variable I'm going to eliminate. What do we want this coefficient to be? Well, we want it, the easy way to think about all of it is if we made it whatever the least common multiple of our given coefficients are. So the least common multiple of 5 and 2. One easy way to figure out any multiple of 5 and 2 is just to multiply 5 times 2 together. 5 times 2 is 10, and 10 does happen to be the least common multiple of 5 and 2. So if we made this negative 10 and this positive 10, that would be able to eliminate x. So how do we get negative 10 from negative 5? We're going to multiply this by 2. But we also have to do something to the second equation because the second equation doesn't have a 10x either. But how do we get from 2 to 10 by multiplication? We're going to multiply by 5. All right? So everything in the first equation is getting multiplied by 2. And everything in the second equation is getting multiplied by 5. So where does that get us? That gets us negative 10x plus 4y equals 64. And 10x plus 15y equals 50. All right, so that's why I pulled out my calculator earlier. I knew I was going to need it. Negative 10 and 10 are going to cancel. Sorry, I had to pause this for a second. I don't remember what I was saying. The 10x is cancel. Okay. 4 plus 15 is 19y. And then 64 plus 50 is 114. So divide by 19. All right. It does work out evenly, luckily. Y is 6. And again, we're going to plug this back into either one of the two equations. Doesn't matter which one. I'm going with the second one just because the numbers are slightly smaller. 2x plus 3 times 6 is equal to 10. So this is 18 minus 18. Negative 8 divided by 2. X is negative 4. So we're going to write our final answer again as an ordered pair. Negative 4, 6. All right. I want to do a few more just so we kind of get the hang of it. All right. Actually, for this one, I want to talk about, like, okay, I know it's probably easier to pick x as the variable to eliminate because it's like I was saying before, they already have opposite signs. But there might be a situation where every single sign you see is positive, or every single pair of x's and y's has the same sign. You know what I'm saying? So let's just pick y. All right? Because we're going to have to do some slight extra work in order to get y to not only have the same same coefficient, but opposite signs. What is the least common multiple of 2 and 1? Well, it's 2. So we want both of those to have a coefficient of 2. One of them has to be positive and one of them has to be negative. It doesn't matter which one. Since this one already has a positive 2y, we're going to leave it alone, kind of like we did a couple problems ago. So if this is positive 2, the coefficient in front of y, I can't like do this without not having votes. The coefficient in front of this y down here has to be a negative 2. So in order to get from 1 to negative 2, we would have to multiply the second equation by negative 2. Technically, it is completely fine if you multiplied this equation by 2 and the first equation by negative 1, because again, it doesn't matter which equation is positive and which is negative, but we're kind of killing two birds with one stone if we just work with one equation and multiply it by negative 2. It's also a little bit easier just because you don't have to do as many multiplications. All right? So if we do that, the second equation gets us positive 2x minus 2y equals 4. And since we worked with the second equation, just for the sake of organization, I'm going to rewrite this first equation right below it. 3x plus 2y equals 6. And then it's a lot clearer to say, okay, negative 2 plus 2 cancels out. 5x equals 10. Divide by 5. X equals 2. And then same thing. We plug into either one of the two originals. I'm still sticking with the originals, again, just for the sake of organization. Smaller numbers in the second one, so that's what I'm going to go with for plugging in. Negative 2 plus y equals negative 2 plus 2. Y is 0. This is possible, all right? If you get a 0 as either one of your x or y's, it doesn't mean there's no solution, all right? 0 is a possibility for a numerical solution. 2, 0 is a point. So 2, 0 is a perfectly acceptable answer for something like this. All right? We'll see what okay. I think this is actually the last one that I have here. All right, we have a lot more freedom than anything, I think, than any problem that we've seen so far, because both the x and the y already have opposite signs. So that's half the battle. So we can pick really whichever we want. Now let's kind of take both cases into consideration. What would the coefficient have to be for the x's? What's the least common multiple of 2 and 3? It's 6. What's the least common multiple of 5 and 4? 20. In the grand scheme of things, it really doesn't matter which x and which y you pick. Personally, and I think you guys might be in the same boat, 6 is smaller than 20. So if my coefficient is going to end up being 6, those numbers are going to be a whole lot smaller than the ones I would get if the main coefficient was 20. So I'm going to go with the 6, which means I'm going to go with the x's to eliminate. All right? So we'll keep this positive, we'll keep this negative. Again, how do we get from 2 to 6? We're going to multiply by 3. How do we get from negative 3 to negative 6? We're going to multiply by 2. And so 6x plus 15y is equal to, what is 26 times 3? 78. Okay. And negative 6x minus 8y is negative 50. Okay. So the x's get eliminated as we expected. 15 minus 8 is 7y. and 78 minus 50 is 28. So I think we solved something like this before. This is 4. Again, the second equation, the numbers are slightly smaller, so that's what I'm going to go plug the 4 into. Again, it does not matter. You should get the exact same thing regardless of which equation you plug into. So negative 3x minus 4 times 4 equals negative 25. So this is negative 16. Plus 16 is negative 9. Negative 9. Divided by negative 3. X is 3. So 3, 4 for that last problem. Awesome. All right. And the only other thing that's here, right? Let me just flip through this real quick. Yeah, the only other thing that's here is just a quick little showcase of all the different methods of solving a system, any system of equations. All right. We talked about graphing a really long time ago, so like this little unit is really just going to focus on substitution and elimination. We're actually going to talk, I think I have a whole lesson set aside for this, about which methods are best for which situations. So we're going to get into that in a lot more detail, I believe sometime in the next few days. But this is just kind of, it's just nice to have if you want to reference it for that eventual lesson or whenever. And yeah, that is it for today for solving systems of equations by elimination. There's plenty of space on the sign-up sheet for video calling if anybody is interested in, or if anybody needs help and is interested in like doing a face-to-face kind of thing. You have homework on this as expected. Please, please, please show all your work. I think I said this when we first started talking about systems. There's a lot of work for these kinds of problems, no matter which method you do. So there's really no way to kind of get out of doing all that work. So I want to see all that work. Make sure you're understanding it by doing all that work. All right? And I think that's it. I think I'm rambling too much anyway, as per usual. I hope you guys are staying safe out there. And I will talk to you very soon.